Hey everyone, before we get started, I want to make an announcement. So on Thursday, Hackers at Berkeley is going to be hosting a workshop on Apache Mesos. Apache Mesos is a sort of a distributed computing framework that a lot of companies use to run different tasks and jobs on clusters of computers, and basically it makes your life a lot easier by like handling shared resources and stuff like that for you. A lot of companies use Apache Mesos to deploy Spark and Hadoop, for example. I think Twitter does that and a bunch of other companies. So the project came out of Berkeley, so we're going to have a bunch of engineers, a lot of them Berkeley alumni, from the Mesosphere startup that formed around this project, and they'll be leading the workshop on Thursday. I'll be posting details on Piazza, so if you're interested, check Piazza. Thanks.
All right, thanks. Yay. It's great to see Berkeley open source, coming back to Berkeley. It's awesome. So before we start lecture today, I wanted to take a moment. This only happens there's only been 3 Turing Awards ever given to database people. This is number 3, and it's sort of a big deal. And even better, the work that led to this Turing Award was done right here at Berkeley. So Mike Stonebreaker is this year's Turing Award winner. He was a Berkeley professor for, I think it was 27 years or something, before in the early 2000s he retired to MIT in Boston. He was the person who started CS186. He used to be the main instructor for the course. And many of the ideas you learn in this class were invented by him, or were refined by him, or were certainly influenced by him. He's been a real leader of the field. So I thought I'd take 5 minutes and tell you a little bit about Mike Stonebreaker. He was also my master's thesis advisor here at Berkeley in the early 1990s. And I certainly owe him a debt of gratitude for that. So just take a minute. This is the guy, the citation for fundamental contributions to the concepts and practices underlying modern database systems. So that's the official ACM citation for this year's Turing Award. He was also a pioneer and a role model for open source. This is the first Turing Award, I think, that makes explicit mention in the details of his contributions in open source. So it's kind of hard to believe that there hasn't been a Turing Award where part of the conversation was around open source, but it's actually true. And he's a serial entrepreneur and a parallel entrepreneur, actually, as you'll see. So kind of a role model for that as well, and unusual in his day as an academic. So here's the full citation, which I won't read out loud, but I'll highlight some of the details. Ingress was one of the earliest relational databases built, and it was built here in Berkeley as open source. Introduced the notion of query modification used for integrity constraints and views. 2 things you learned about in this class were pioneered in Ingress. As you know, Postgres, which is now PostgreSQL, was the post-Ingress project and was the first data management system to introduce abstract data types into the database system. I'll talk about that in a bit. In the citation, it talks about releasing these systems as open software, which allowed their widespread adoption. And it is absolutely the case that those code bases have been incorporated into many commercial systems. The number of systems built on Postgres is large, and many of them are very influential systems today, like Amazon Redshift, for example, is built on Postgres. Blah, 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 blah. And then, in recent years, he's been very active. Is credited as one of the people invigorating the idea of column stores, which has been a hot topic, scientific databases, and other fields as well. So let me give you just like a real brief history of his career, because it's kind of interesting. So there's the guy in the 70s. Love this photo. It's interesting to see how like one of these folks, ran their life. So he arrived here as a junior professor right out of grad school. He started working on something that was supposed to be an urban planning project. There was no field called databases in academia back then. And he started designing this thing called the Interactive Graphics and Retrieval System, which is what Ingress was. And he ended up being sort of one of the flag bearers for relational databases being a practical thing back in the 70s. And that was considered very academic and impractical at the time. Relational databases were considered very mathematical and impractical. He sort of fought this war alongside colleagues at IBM, namely the System R group, about which you've learned. It was something of a friendly competition. Those folks all remained close over the years. Ingress was an open source system, and it ran on Unix, which was a pretty brand new operating system at the time as well. So it was one of the few things you could get that really did anything interesting on Unix at the time. And a lot of universities and companies that were experimenting with Unix went and experimented with Ingress too. He started a company in the early 80s to commercialize Ingress and battled famously with Larry Ellison for dominance in the field, and of course did not defeat Larry Ellison, but had a large impact nonetheless. And his students founded a bunch of other companies, including Sybase, Tibco, One of his students was the founder of VMware, Diane Green, and there's a number of others. So very entrepreneurial. Ingress was actually bought and sold a few times. It still exists. It's owned by a company called Actian. In the 80s and 90s, he kind of did the same thing. So he did the Post-Ingress project, which was Postgres. And the theme with Postgres was, two things, really. One was to move code to data rather than pull data out of the database and then have code run on it. So this is, essentially where big data came from, the idea of pushing functionality like map and reduce, those sorts of things, near to the database, near to the data storage system, was pioneered in Postgres. So there were user-defined types and user-defined functions in this system. The query optimizer, actually more advanced in a lot of ways than today's big data systems. The query optimizer knew about these functions and would optimize queries that contained functions in special ways. And I didn't even teach you about this stuff because it's still considered advanced material. There were these active rules you could register with the database that would say, if a certain thing happens to the database, then go do this or that. And then it was an early system to explore the idea that, look, it's a database. Why would you ever delete anything? Let's just keep all versions of history forever, and then you can run queries over the past. And this was an idea he was exploring in the 1980s when storage was, relatively speaking, extremely expensive. So it was very far ahead of its time. PostgreSQL, which you all know about, was an effort started by a couple students in the group to port SQL, the SQL syntax on top of Postgres, but that port was then picked up and extended outside Berkeley by a global community. He founded his second company, Illustra, which was really Postgres Incorporated. It was bought by Informix. They again took on Oracle. Oracle again was in significant competition. There was a time in the late 90s where it looked like Oracle might actually go bankrupt. And part of that was that Informix was coming at them real strong. Oracle obviously survived that and became even stronger. Informix got bought by IBM and is still a product there. And all of that technology around Postgres, in a lot of ways, was washed over by the web. And for many years, people weren't worried about pushing functions into data. They were worried about HTML pages and crawlers and search. So this all only come back in the last, say, 5-10 years. In the 90s, he worked on a federated database system called Mariposa, which had an interesting query optimization model based on economics. Started his third company called Cohera, where I was involved as well. It was a very good learning experience for me. That company was bought by PeopleSoft. And he was also one of the first people to work on data visualization. So he had a system called Tioga Data Splash in the 90s that was, again, commercialized. And around 2001, he retired to Boston because that's where his wife was from. And they gave him an adjunct position at MIT. And his sort of time between research project and startup company started shrinking exponentially to the point where he currently has 3 parallel startup companies going based on his research at MIT, some of which there wasn't much research. And there's 3 companies that he's already built and sold in that period of time. So the most successful of those was Vertica, which was based on the CStore project, which is a column store database. Vertica is still widely used. It was bought by HP for a handsome sum. The others were smaller. But there's a guy who's now, he's got 3 companies now. He's done 6, 8, 9. I think started 9 companies, each of which was at least moderately successful over the course of an academic career of 40 years or so. So a very interesting guy and an unusual model for how to have impact both as an academic and an entrepreneur. So that's this year's Turing Award winner. There's going to be a award ceremony next month, I think. And then if any of you want to go to the VLDB conference, which will be in Hawaii in September, which would be very nice to attend, he's going to give the Turing lecture there. So it's been a fun year for those of us in the field. All right, so that's just a little fun news from the street. By the way, the only other there were 2 other Turing Awards to database. The first one was to a guy named Charlie Bachman, which was in the 70s. He's one of the folks from the pre-relational days, was very involved in hierarchical databases and something called Codicil. And then Jim Gray, who's sort of considered the father of transactions, who was part of the System R group, won the Turing Award in the 90s, late 90s, I think. And Jim Gray and Mike Stonebreaker were very close colleagues and friends. And so it took another, I don't know how many years, 12 years or so, till Mike was honored as well. All right, so when we left off a week ago, we were looking at some advanced topics in concurrency control. And I wanted to actually finish those. I think we have time. Just to give you a landscape, we only have 4 more lectures. Okay, there's this week and next week. Thursday is the faculty retreat, which is a sort of Harry Potter-esque meeting of wizards. that happens far, far away, and nobody knows where. We discuss wizardly things. But I will be missing class on Thursday. So I have a guest lecturer coming in, a guy named Ty Rattenbury. Ty's a data scientist and has been for some time. He works at my company, Trifacta. Prior to that, he was a data scientist at Facebook. Prior to that, for a consulting firm. And prior to that, at Intel. And before that, a PhD at Berkeley. So widely experienced dude. He's going to tell you guys kind of what it's really like to be a data scientist and what that might mean today as that field is evolving. I think it should be pretty interesting. The other thing to know about Thursday is that at the beginning of class, before Ty's lecture, is the HKN evaluations. Please do come and fill those out. The university likes to see good return rates on those just to make sure that students actually take classes and professors actually teach them. So it'd be good to have you all come and give me your feedback. I'd be grateful as well. I learned from those. And then next Tuesday, so today we'll finish this topic and start logging and recovery. Next Tuesday, we'll finish logging and recovery. And next Thursday, the final lecture will probably look at distributed systems, NoSQL, and the like, okay, and replication of data, essentially. And that'll be the last lecture. So we're winding down. Okay. Oh, and by the way, midterm grades should be back today, I think is what we decided. So we're just about done grading them. We have to get them into GLOOKUP for you. It should be done today. All right. We left off last time. We looked at B-link trees, and then we talked about phantoms. And I got a real good question in office hours today about phantoms, so I want to revisit them briefly. If you remember correctly, we had an example of what a phantom was last time. And I want to clarify this example with a little bracketing of where the transactional boundaries are, because that's the key piece of information that's missing in this example. So imagine that you have two transactions, T1 and T2, just like in this example. And here's how this is going to look. I'm going to give you a sort of loose version of a schedule. T1, in his application code, is going to say begin transaction, which is a command you can type to Postgres or any database. And then everything that you type after that is supposed to be the same transaction until you say commit. Right? So he says begin, and then he queries for sailors with ratings between 5 and 8. So he runs a query, rating greater than 5, rating less than or equal to 8, greater than or equal to 5. So he runs this query, and he gets an answer. And let's say the answer has 10 tuples in it. So he reads 10 tuples. Okay? And because there's a B tree on this table, he's able to read those 10 tuples and no other tuples in the table. So he doesn't scan the table, doesn't read anything else, and doesn't get, therefore, table level lock. So just gets 10 tuple level locks. Meanwhile, T2 comes in and inserts a sailor with rating equals 7. All right, and by the way, T2, begin, insert, commit. All right. Now, there was no tuple with a rating equal to 7 prior to this, and therefore this guy didn't get it in his answer, and also didn't lock anything with a rating equal to 7 because there was nothing with the rating equal to 7 in the database at that time. Now, if he runs his query again, rating greater than equal to 5, rating less than or equal to 8, he's going to get all 10 tuples he got before because they were locked, and he will find a new tuple that wasn't there before, which is this tuple. He couldn't have locked it before because it didn't exist, right? That's why it's a phantom. All right, and then he says end transaction. And if you don't do phantom handling correctly, this just all happens, right? These transactions commit, and strangeness has occurred. Note that this is not serializable in the sense we discussed. That is to say, there's no ordering of these two transactions in which T1 gets different answers to the same query, right, when he runs it twice. So something's funky, right? So that's what a phantom is, and the reason it arose is prior to thinking about this, we didn't assume that the database could change. So what we need to do somehow is lock the output of this query, right? And that's what the next key locking trick does. All right, is it outputs a range of values. So remember, and there's a different example on this slide. In this example, the query is just for 7. And the mechanism is, if you want to query for 7, you lock the next higher thing if 7 isn't there. In the B tree, you lock 8. Okay? And then if somebody wants to insert the value 7, they would have to get an X lock on the next higher value, which is 8. And they would collide with your shared lock here and have to wait for you. Okay? So that's the trick with next key locking, is you effectively use the next highest value that's been stored as a surrogate for the entire range, in this case between 5 and 8. By locking 8, you've successfully locked the range 5 through 8. Anybody who tries to insert between 5 and 8 is going to go check 8 for a lock and wait on it. Okay, so that's phantoms and next key locking. And by the way, if there weren't an index to begin with, we would have scanned the whole table and gotten a table level lock, and then phantoms couldn't have happened. So that's the other thing. If there's no B tree, this problem just doesn't arise. Any questions? Cool? All right. So, a couple more topics, advanced topics in concurrency control I wanted to go through. And this is a whirlwind tour. So, B-link trees we did in quite a bit of detail. Phantoms we did in enough detail that I think they're perfectly understandable. There's no more detail you really need. Multi-version concurrency control, I'll give you the basic idea. Distributed concurrency control, I'll give you the basic ideas. And weak isolation, again, sort of just the basics. So the rest of this stuff is a bit of a survey, but I think it's useful to know about. So there's an alternative to two-phase locking, which is called multi-version concurrency control. And the version we're going to look at, the kind of multi-version concurrency control we're going to look at is timestamp ordered multi-version concurrency control. And it's a really elegant scheme. All right, so here's the basic idea. Every transaction, when it enters the system, is given a timestamp, which is a monotonically increasing value. All right, it could be the wall clock time, but wall clock times can be screwy because people can reset the clock. It's a monotonically increasing value, like a query number. All right, or sorry, a transaction number, not a query number, transaction number. So when you come in, you get a timestamp. And then here's what we're going to do. For every data item in the database, we're going to keep some timestamps on the data and some versions of the data. So every time any transaction reads that data item, we will make a note of that next to the data item. We'll record that it had a read timestamp, and that timestamp will be the timestamp of the transaction who read it. Because remember, every transaction gets a timestamp. So we have a set of read timestamps associated with every data item. And we'll also have a set of versions for every data item. And the versions will contain a write timestamp, which is the timestamp of the transaction that generated that version. Okay? So the algorithm for reading things is really easy. If you want to read something, and you have timestamp TS, what you do is you look for the version of that object X that has the largest write timestamp, less than your read timestamp. You want the most recent version from the past, where the past is defined by your timestamp. Right? So you find the largest write timestamp less than your timestamp, and that's the version you read. And don't forget to add your read timestamp to the object, to X. Okay? So that's reading. Find the most recent version before you, and then make a note that you took the read. Reading always succeeds. So a read-only transaction is guaranteed to commit, which is nice. Okay, that's a really nice property. Read-only transactions, which after all aren't causing any trouble. They're just minding their own business, reading things, right? They can always get versions of data that are the correct versions for themselves, and off they go. So that's pretty cool. Can't do that with two-phase locking because we lose the old versions and we set locks and all that. Here we keep all the old versions. You just find your point in time and you read your stuff. Very nice. Writers have to be a little careful, though. So if you're a writer at timestamp TS, that's your timestamp of your transaction, you want to write the value V into object X. Here's what you do. First of all, there's an interval we'll define, which is the interval from your timestamp, your point in time, to the minimum of all the write timestamps after you. So it's the interval in time from you to whoever was right after you in the right ordering. Now, that might be nobody, but there might have been somebody with a higher timestamp than you that wrote a version of this object, okay? So that interval is from you to the next higher person. If there's a read, I got it backwards. It's the person most recently in the past. Let me do that again with my hands. Timeline is going this way. The interval is from you. No, I had it right. There's pictures on the next slide. That's the most annoying thing. I wanted to say this and then show you the example. Yes, that's right. Interval is from you to the next person after you. That's right. If somebody did a read in between where you want to do your write and the next guy, somebody already did a read in there. What did they read? They read the version before you. Okay? So you're going to jump in. They came after you to do a read, but they actually got a version from before you. You would have to go and fix up their read. They should have read your version, because your version is right before their read, but instead they read the version to your left. Okay? Which means that, well, you can't. You can't go fix up their read, because reads always win. So you have to abort. Basically, you're too late. Your write is coming too late. Somebody already read a value that should have been you, and you showed up too late, so you have to abort yourself. But if that's not true, then you just create your version and add the write timestamp. So new writes check to see if they arrive too late to affect a previous read. And let me show you an example of a timeline. Time is going to go from left to right on the board. This is a single object, okay? And there's values for that object, v1, v2, v3, etc. Values are associated with write timestamps. So v1 was written at time 5, v2 was written at time 10, v3 at time 20. And remember, those timestamps are just the timestamp of the transaction that did the write. So what I said was technically not right. What I should have said was v1 was written by the transaction with timestamp 5. v2 was written by the transaction with timestamp 10. v3 was written by the transaction with timestamp 20, etc. Okay? And there are read timestamps that have been stored for this x. So somebody with timestamp 7 read this object. Somebody with timestamp 92 read this object, etc. Now, if somebody with timestamp 95 comes in and wants to read the object, what do? They look in there and they say, what's the biggest write timestamp less than 95? It's 92. So the version I'm going to get is vn minus 1. All right? And I have to make note that I did a read at 95. Okay? So that's what happens for read x at 95. Everybody with me? All right, now somebody comes along and their transaction with timestamp 93, and they want to do a write. Okay, what's the interval for 93? It's 93 to the next largest version, which is 100. Okay, and then they ask, were there any reads between 93 and 100? And the answer is yes, there was 95. Now that first guy, if things had happened in a different order, would have read this version at 93, right? But we're too late. The 93 write is too late to affect that previous read from a different transaction. And so that guy has to abort, because it would invalidate the 95 read otherwise. Note that these two lines are from two different transactions, right? One is the transaction with timestamp 95. The other is the transaction with timestamp 93. They're different transactions. Why do we keep around any read timestamps except for the last one? Anybody want to try to answer that? Yeah.
What are the last ones after 100? Then you wouldn't realize that someone has read after you.
Say that again?
If the last read timestamps after 100, then you won't know there's a problem.
If the last read timestamp were after 100 in this example, who wouldn't know there was a problem? 93? Well, he would know the problem. Oh, I see. Yes. Good. That's fine. We do need to, so in this example, I think let's try this. I think you got it. In this example, 93 comes in. If we only kept the last read timestamp, right? And it was 102, would it be a problem for 93 to do its write? Actually, no, because 102 should read 100 anyway. But if there was a read, this is interesting.
But the read at 95, our record would look like that it got the version written in 93 when it actually read the version written in 92.
That's true. I think let's look at this from a different point of view. Suppose that somebody was really a long-running transaction here, and they came in and they read 17, or they were transaction timestamp 17, okay, in this history, and all we kept was 95 was the latest. Should 17 Okay. No, that's fine. It's the write. It's a write at, sorry. If somebody did a write at, say, 14, okay? Somebody came in to do a write at 14. They're a long-running transaction. They've been around since 14. They're still going, and they want to do a write at 14. And all we've remembered is 95. What we don't know anymore, because there's a write at 20. Clearly 95 doesn't depend on the write at 14. It got overwritten by other stuff, okay? Does anybody depend on that write at 14? Yes, the guy who did the read at 15, all right? So we need to keep him around in case there's any writes between 10 and 15. Does that make sense? Good. So the nice thing is that writes can kind of mask the previous writes. That's why intervals only define to the next write to your right. If there's things that happen after that, they read that guy, so they didn't read you. But you do have to keep all the reads to fence in those inter-write fields, because the readers can be really old. Now, one of the things we're not going to talk about here is in any scheme like this, there's a garbage collection problem. You don't want to keep these versions and timestamps around forever. Okay? And so you have to think about, gee, when can you age out these timestamps? You know, there's no one else that's valid. And maybe if there's a super long-running transaction that's keeping you to keep timestamps, you should just abort him because he's causing trouble. So there's a lot of details. But this is the basic idea. Question? If the transaction with the read already finished, all the more reason you can't allow this write to happen, right? Because the transaction with the read can't even be aborted. So the deal is readers always win. They always can finish. Writers always check to see if they can legally do their writes, and writers will abort themselves, right? Well, in this example, maybe let's clarify. In this example, 93 is going to be aborted, which means that 95 really did read 92. There was no 93. It's like there never had been a 93. 93 is going to abort. In a universe in which 93 committed, it should have read 93. But we won't allow that universe to happen because it's too late to set that universe up. 95 is already committed and it's gone. And so 93 can't exist. It's no worse than, say, what we get with deadlock and two-phase locking. It's like, in principle, you want all those transactions to complete, but you're going to abort one of the transactions on the deadlock cycle. It just happens. Sometimes the database aborts things. Okay? So, one of the trade-offs you have to think about is you can ask yourself, is two-phase locking better than multi-version concurrency control from a performance perspective? Two-phase locking will abort things less, but it has locking. This thing, nobody ever waits for anybody, but there's maybe a higher abort rate for writers. So there's a bit of trade-off there, and it's tricky to know which one's going to win. In the past, it was found that two-phase locking is more efficient than multi-version concurrency control for a bunch of reasons. In the present, that is much less clear. So let me take you through, at a high level, some of the pros and cons of multi-version concurrency control relative to, say, two-phase locking. So good things about multi-version concurrency control, you get a higher degree of concurrency. More readers can go through this, for example, without waiting than in two-phase locking, because readers never wait in MVCC. Read-only transactions do no extra work. They don't even set locks. They don't manipulate the lock table. They just go. So if your main concern is that reads should be super fast, this is quite nice. Okay? Writes are sort of append only. You never mutate anything. So it kind of feels less, there's less conflicts on writes, bottom line. You'll even write conflicts are less. Okay? So those are all good things. Mixed things, well, maybe there's pro, maybe there's con. You don't update things in place. You keep versions of everything, right? So what's good and bad with that, well, what's bad about it is that if you don't update things in place, things have a tendency to move around. The latest version of an object may not be in the place where the previous version was, which means it might not be next to the other things it often gets queried with. So you have to work kind of hard to achieve data locality for readers, to make sure that readers have all their objects together. You end up kind of shuffling data around. And that traditionally has been expensive. Same problem with log-structured file systems, if you've heard of this. Any multi-version scheme for storage often has problems making sure that the versions that tend to get read together get stored together. Okay. one thing that might be nice or might not be nice, depending on how you look at things, is that you have the history of data objects, usually near the data objects, although it's up to you where you place that kind of stuff. But it might be nice to have the history of objects, right? And you might be able to expose that in a query facility. So you can ask questions in the past, or you can ask questions across time, right? Those facilities suddenly become possible in this kind of a storage system. But it is hard to make all that stuff efficient. I'm not saying it's impossible, but it's hard, particularly on magnetic disks with high seek costs. Right? Data locality is so super important on magnetic disks. And then what's bad about this stuff, you have to deal with garbage collection of old versions. If you care about your storage is limited, you're going to have to throw away some old versions. When is it okay to throw them away? And then remember that we're not locking, so we never wait. Instead, we abort or restart transactions. And that could be expensive because any transaction that aborts, all the work it did up to now is wasted work. Right? So that can lower the throughput of your system. Some of your scarce resources are being used for transactions that eventually abort. So a high restart rate, or a high abort rate, if you want to call it that, can be a source of inefficiency. All right? Whereas maybe waiting sometimes is less expensive because you wait, but eventually you do good work, useful work. All right. That said, I would say that the wind is blowing in MVCC's sails. So a lot more systems these days are beginning to look like multi-version concurrency systems. And the reasons for these are changes in technology. So Flash, for example, means that data locality is less important. Random I/O and sequential I/O on Flash devices are pretty much the same cost for readers. Okay? So that changes the game in terms of having to organize and reorganize the data. If you have an in-memory database, and after all, RAM can be pretty big these days. We talked about this like in the first or second lecture. We're finally getting the payoff a little bit of this observation. If everything's in memory and you're essentially building an in-memory database, things like lock table management become your bottlenecks. So your CPU costs of things like locking can be quite significantly expensive. So people designing in-memory databases are looking for ways to avoid things like locking on tuples. And one really good way to avoid locks entirely is to use MVCC. Readers set no locks. Readers don't even check for other concurrent transactions. Cheap storage makes version history maybe worth keeping, and maybe even exploiting for these time travel queries or for auditing the past. Sometimes for compliance, you need to keep an audit log of all versions of your data. And then here's an interesting fact about the protocol for multi-version concurrency control that we saw. Other than assigning timestamps, which has to be done uniquely, all right, and that's the only reason this all works is because timestamps get assigned uniquely. They don't actually have to be assigned in order, by the way. You could come into the system, I could give you a timestamp from 3 years ago. And if we kept all the versions, you would be able to run your transaction, maybe. All right, your write might be more likely to cause a problem, but maybe not. All right, so there's no reason we have to assign timestamps in the order of arrival of transactions, just to be clear. But we have to somehow give these timestamps out and make them unique. Other than that, though, there's no other communication between transactions. They kind of do their own thing. They never wait for any other transaction to tell them anything. They just look at they run unilaterally. So there's no coordination with other transactions, and this is super important in a distributed context because it means that you can run your piece of your transaction on this machine without talking to any other machines, no communication cost. That is not true, as we'll see in a minute, in a distributed two-phase locking system. All right. And so there's been clever use of these kind of schemes in a bunch of recent systems for distributed systems and for high-performance main memory systems because you can get coordination-free. And by the way, recent work at Berkeley, one of my students worked on, shows that actually in many cases you can get coordination-free and restart-free, meaning abort-free consistency in distributed systems using a version of multi-version concurrency control, not for serializability, but for something that's almost as good that does things like it'll maintain invariants like key foreign keys constraints can always be maintained using a scheme like this. So if all your C and ACID, all of your consistency invariants are key foreign key invariants, that's all you have, you actually don't need transactions. You can get away with this slightly lighter thing called ramp transactions, read atomic transactions. And those can be implemented in a multi-version scheme like this without any coordination, without any aborts. So pretty cool. Anyway, bottom line is keep your eyes on this space. I taught you the Bible, which is two-phase locking, but you should be aware that if you're designing your own system or you're working with creative people, this is being aggressively revisited. And multi-version concurrency control is kind of the scheme that is most promising from the past. Okay? You will hear out in the field people talk about optimistic concurrency control. This is an optimistic scheme in the sense that it doesn't set locks, and it may abort if it runs into trouble. But usually when people say optimistic concurrency control, they mean a different specific protocol, not this one, which is not as good, frankly, as multi-version. So I didn't teach you optimistic concurrency control. I taught you something better. But a lot of times people out in the field will say, oh, there's locking, but you should do optimistic concurrency control. And you should say to them, well, no, I know what you're saying, but what we should be thinking about is multi-version concurrency control. And you can read about optimistic concurrency control if you like. It's another idea from the late 70s, early 80s in this vein. Okay. Questions on MVCC? Postgres has a version of multi-version concurrency control in it, actually. Oracle does as well in a funny way that we'll talk about in a little bit. All right. With that, let's talk about distributed concurrency control for a second, particularly serializability and two-phase locking. So set aside multi-version for now. Put your head back in two-phase locking. How do we get transactions to work in a system with lots of computers, right? We've done this for query processing. We said, oh, it's easy to parallelize hash join. You just put a hash function on the number of mod the number of machines in front of every tuple, and then you just spray the data across the machines, right? We talked about that. But what about updates? What if one of the machines has some writes on it, and another machine has some reads on it? And how do you make sure you get serializability across all these different machines? All right, it's a well-studied problem from the past. So consider a parallel or distributed database, call it what you will. So one that handles updates. So not like MapReduce is a read-only system typically, but NoSQL systems have this flavor, and distributed SQL systems have this flavor. Now let's assume for simplicity that every transaction when it comes into the system is assigned to one particular node as the coordinator for that transaction. All right? The pretty reasonable assumption. In a lot of systems, there's one coordinator for all transactions, but we could be a little looser than that. We could say every transaction has some coordinator node. Right? Where do we put the concurrency control state for this distributed system? Where's the lock table for two-phase locking? Or the timestamps for multi-version concurrency control? Well, it turns out the answer is really simple. Just keep the locks or the version numbers on the machines where the data is. Remember, we partition data in these parallel systems, say by a hash function on one of the attributes, or by a range partitioning of one of the attributes, right? You can take the sailors table and hash it by sailor as ID to different machines. Well, if you lock a particular sailor, you should make note of that in the lock table at the machine where that sailor is stored. That's all. It's that simple. So basically, you take a traditional database at every node. Every node's got a subset of the data, and every node's got a subset of the lock table. And the locks that are associated with the data are co-resident with the data. All right? So in essence, these are just plain old single-node databases doing their own thing, setting their own locks on their own data. Really easy. All right? Requires exactly 0 changes to what we've said so far, except at the end of the transaction. Well, there's 2 places where we have to make changes. So every node does its own concurrency control. What could possibly go wrong? There's 2 things that could go wrong. Anybody guess what they are? Or maybe knows what they are from another class? That's fine too. Raise your hand. Yes?
If you're trying to duplicate your data across nodes, you end up with inconsistencies.
Oh, okay, so that's a third thing that could go wrong. Good. So if you replicate your data, not just partition it, but have multiple copies of each tuple, then maybe it's complicated, right? Because now there isn't one place to set that lock. There's k places to set that lock. And in many systems that choose to be implemented that way, you get potential inconsistencies among the replicas. Now, a simple thing to do is you lock all the copies. Every time you do a write of a version, you lock it. And then you actually pretty much just get this. So that's fine. But most systems don't choose to do that. We will talk about that the last day class. So assume no replication of the data for the moment. What other problems might arise? Yeah. Absolutely true. One transaction can touch and even update data across multiple nodes. In fact, multiple transactions can do that. And what problem could that cause? Or what problems could that cause? So far, that sounds like that might be okay. But that's the crux of it. What kind of problems happen when you have transactions across multiple nodes? Great. So if you abort in one place, you'd better abort everywhere else. Otherwise, we're not achieving atomicity, right? Similarly, if you commit on one node, you better commit everywhere else or we won't achieve durability, right? So that is one of the key problems, is all the nodes in the system must agree on the commit/abort state of each transaction. Right? So we'll talk about that. That's one problem. There's a second problem maybe somebody can think of. So let's take the example we were given. I have a transaction that's taking out locks on multiple different nodes. You have a transaction that's taking out locks on multiple different nodes. What could go wrong as we're sitting there holding our locks? Somebody said something. All right. What do we worry about with two-phase locking on a single node? What was one of the special things about two-phase locking that could be problematic? Yeah. Cascading aborts, great. Why would we possibly abort a transaction and cause cascading aborts, other than the user asking to abort the transaction? Why do we abort transactions in two-phase locking? Good. So somewhat separate point, but well taken, is machines can fail in a distributed system, but the system's still up, right? And this relates to the previous comment about everybody commits or everybody aborts. If one of the machines isn't answering the phone anymore, what do, right? Because everybody else has to decide whether to commit or abort. And so that'll be part of that process of deciding commits and aborts. But you were on the scent of what I was looking for. Yes. Aha, deadlock. So that's the topic I want to talk about. And then the question was, would you have higher probability of getting deadlocks? I don't know about that, because you could take the same data, the same queries, and put them on one machine, and it would be the same sort of workload. The queries would go faster, so maybe they'd race past each other faster. But deadlock can certainly happen. Now, is deadlock any harder to deal with in a distributed system than in a single-node system? Well, what's our scheme for dealing with deadlock in databases? Do we avoid deadlock? Do we prevent deadlock? What do we do? We detect deadlock, right? And then we shoot a transaction. I think it's in the song. Yo. So how do we detect deadlock in a distributed system? Is it harder? Where's the waits for graph? It's all over across multiple nodes, okay? Because you may be holding a lock here, and I may be holding a lock there, and you're waiting for me here, and I'm waiting for you, well, the other way around. I'm waiting for you here, and you're waiting for me there, right? And the only way we'd know there's a deadlock is if we look at here and there together. And so we do have to deal with distributed deadlock detection, which isn't really that bad, okay? So every node does its own concurrency control. We could get distributed deadlock. How do you resolve it? Have everybody send their piece of waits for graph to one place. It's not that much data. Right? And then you gather up all the edges, union them together. Now you've got the full waits for graph, and you check for cycles. Right? So that's easy. All right. Message failure and delay. You guys talked about that. Node failure and delay. All right. Those are things that can happen. And then just plain old commit abort decisions. So how do we decide on committing and aborting, especially in the face of messages and nodes failing or being delayed? And by the way, there's a theorem from distributed computing that you can't distinguish failure from delay. Okay. Too general problem. Go read about it. It's pretty cool. We won't do it in this class. So how do we implement this? We're going to have a vote. All the machines in the system get to vote on whether the thing should commit or abort. Okay? How many votes does a committer need to win? What kind of vote is this? What's the rule for committing? Is it a majority rule democracy? Is it what is it? What kind of votes do we need? Can any one node veto? Yeah. All right, so the argument is everyone must vote to commit, or anyone can veto. Any single computer can veto. Does that sound right? How many people think that's right? Unanimous vote. But we don't all agree, so we can't commit this transaction. So, yeah, it's too meta, sorry. So we'll just have to go with dictatorship. And yes, indeed, it has to be unanimous vote, and it's because I say so. Not because I say so. It's because it makes sense. All right, think about it. If you're a node and let's say you crashed, period, you're gone. You've lost the state of that transaction. We will never be able to make that transaction atomic, right? Because part of that transaction is lost forever. And if you can't make it atomic, you're not allowed to commit. Okay, so even if everybody else is like, this transaction is awesome, I want to commit it, we lost a piece of it. It can't be an atomic transaction. So we certainly couldn't commit under those circumstances. Okay, but there's lots of other reasons. Like one node could detect a integrity constraint violation. Maybe my node says, hey man, foreign key constraint's being violated right here, right here. I get to, we said it has to be consistent at commit time, right? And I'm the one with the evidence that it's not consistent. I get to vote to abort, and then everybody must abort. All right, so you got to have a unanimous vote to commit. How do we implement distributed voting? It's actually kind of a pain in the butt. As you probably know from American history, at least of the 21st century, voting is kind of complicated. Okay, so when you take a distributed systems class, and even worse, a distributed systems theory class, you spend a lot of time voting. A lot of stuff boils down to how do you do different kinds of voting in a distributed system reliably. And the whole problem is that you have messages in nodes that are delayed or failed, and you have to figure out when you can call the vote. Okay? And oh, by the way, the guy counting the vote could also fail. Oh, shit. Right. And it's like turtles all the way down. But the simple protocol that people use in distributed databases, and it's reliable, well, we'll talk about it for a second, is we have this coordinator for the transaction. It's the node that was assigned to this transaction. And the coordinator in the phase 1 of this two-phase commit, by the way, two-phase commit C, 2PC, not to be confused with two-phase locking, 2PL, totally different things. Okay, you can put them together. And in fact, I'm assuming you do put them together, but they are separate things. And it's really annoying to talk to database people. And you're like, yeah, so if you're doing 2PC, you just got to remember which one is which. Okay, two-phase commit. Two-phase commit goes like this. It's got two phases. In the first phase, the coordinator tells the participants to prepare. So that's when the user says to the coordinator, I would like to commit this transaction. The coordinator then disseminates to all the participating nodes in the transaction, prepare. And the participants respond with yes-no votes. Those yes-no votes are their votes for this transaction. If everybody comes back and message arrives at the coordinator from everybody that yes, they were willing to commit, then in phase 2, the coordinator disseminates the results of the vote. Yes or no. All right. And, oh, by the way, things can fail along the way, so everybody has to make notes in stable logs at each node. So both the coordinator and the participants have to write log messages at exactly the right times, and I'm skipping that detail today. All right. Maybe we'll talk about that after we do logging and recovery, which is more like this week. All right, but for now, we'll skip that. Note what this protocol is. So Jim Gray used to describe this protocol as it's like the wedding ceremony. Phase 1 is, do you take this man or woman to be your lawfully wedded whatever? And phase 2 is I now pronounce you man and wife. Right. So this is a classical protocol, okay? And it can be shown to produce the right results as long as the coordinator doesn't fail. Or the coordinator fails but can come back up and recover. There's no way for someone to pick up the coordinator and start over, though, in this protocol. All right. Now, to put it together with two-phase locking is really straightforward. If the messages are ordered in this network of communication, then before anyone agrees to committing or aborting, they will have already got all the locks for that transaction. By the time the user says, please commit, all their writes have been handled, their reads have been handled, all the locks are being held by all the nodes, okay? And if it's strict 2PL in particular, then when the coordinator says commit and pushes that message out into the communication channels, all the read and write message requests were before it, okay? And everybody has all the information at every node they need to decide whether to commit or abort. Okay, so that's fine. And with strict 2PL, you can abort without worrying about cascading aborts also. So this has nothing to do with sort of cascading aborts. It's just the usual deal. Somewhat trickier with multi-version concurrency control, how you do the two-phase commit. I will not go through that today in class. This is kind of enough to make you dangerous in a distributed transaction system. You know what you sort of need to know. Two-phase commit, global deadlock detection. It's kind of all you need if you really want ACID and you're willing to pay for it. Pretty expensive. This is time-consuming. To run a two-phase commit protocol, you have to get all the computers in your network to agree before you can move forward. So you run at the speed of the slowest guy, right? Because you're waiting for that unanimous vote. And if the slowest guy is really slow, that stinks. Okay? So two-phase commit is widely perceived as being very expensive because it's this synchronous global protocol. Everybody must participate, and no one can move forward on the transaction until everyone has participated. It's kind of a drag in that respect. But it gives you ACID. And we will talk more about that in a week when we talk about NoSQL. Okay, last topic, which is kind of comes up at the end of this discussion. So we said acid's kind of expensive, at least in a distributed system. In fact, acid's kind of expensive in a regular system, even though I can tell you that, there are benchmark results with systems like Oracle and IBM DB2 doing tens of thousands of transactions a second, which is a lot of actual transactions when you think about what are transactions for. They're for the really important stuff like purchasing the shopping cart on the website. Even if a lot of people are shopping at once, they're not all pressing checkout, There's not 4 billion people pressing checkout every second. It's not like search, right? It happens less frequently. So 10,000 transactions a second is a lot. But still, transactions are slower than non-transactions, and sometimes that's a drag. And so people have long, since the 1970s, thought about, what would it be like if, we didn't want all of ACID. We didn't want fully serializable transactions. We said something just a little bit less. Let's turn the dial down on correctness just a little ways. I don't want it to go to crazy, right? Don't set it to crazy, but can we set it to 7 on a scale of 1 to 10, where 10 is serializable? What would 7 even mean? All right, so people have thought about this for a long time, and it's usually called weak isolation in the database community. And in distributed systems, you hear people talk about consistency models. These are related but not the same. So today I'm going to talk about isolation, weak isolation, which is actually something that's delivered in lots of commercial database systems. So you should know what it is anyhow. All right, so the motivation is this. Sometimes transactions just seem too restrictive. Like the chancellor requests the average GPA of all students. Does the chancellor have to get the exact average GPA? Come on, not really. If the various professors are making updates to grades, can't you just let those things run at the same time? And maybe the chancellor doesn't exactly see the exact GPA, but all the grades get recorded correctly. So sometimes it just seems restrictive to, while the chancellor's running his report, I can't update your grades. It just seems crazy. All right? And sometimes transactions also seem too expensive in throughput. So the first one is sort of a latency problem. The second one's more like a throughput problem. And the example I gave you in a distributed system especially, it's just two-phase commit requires everybody to wait for everybody else. So must transactions be all or nothing? Can we have loose transactions or maybe just a little bit of transactions, just like sprinkled on top? And the short answer for the rest of these slides is, well, you can, but it's really hard to make sense of what the hell's going on, to be quite honest. Like all the things I'm about to teach you, which ship in commercial database systems, nobody really can reason about them. So application programmers who use these loose consistency modes don't really know what they're getting, and crazy stuff does happen. So the dial kind of is binary. There's serializability and crazy, but we can describe crazy at least at a mechanistic level, and you can decide if it makes sense to you. You'll see what I mean, okay? And many people do adopt a don't worry, be happy kind of attitude about this. It's enough. So we'll see. So SQL actually baked into the standard has this notion of weak isolation levels. And the intuition of it's pretty much based on two-phase locking, okay? This has caused all sorts of nightmares for people who don't implement two-phase locking but implement other concurrency control protocols because the standard isn't really well defined for anything but two-phase locking, which has led to lots of research papers and headaches that I'm not going to go through today. So pretend everybody uses two-phase locking, which is what the SQL standard does. And here's the different isolation levels. The first one's called read uncommitted. And the idea is that this is like mayhem, okay? So this is the dial set to 0. You can read dirty data from transactions that haven't even committed yet. The only thing we promise you is you won't read a torn write. I mean, if you read an object in the database, you do get the object. It's not corrupt, right? But it's not necessarily in any transactional state at all. You're reading uncommitted writes, all right? And so there's no locks for readers is the way you implement that. Readers don't set locks. Writers do set locks, though, so they don't corrupt each other. And one of the properties of all of these is that if you choose to be serializable, none of these other modes, if other people have the other modes, they won't screw you up. Because everybody always gets a write lock. If you're two-phase locking, they will have to wait for you if you hold a read lock. Okay? So all this stuff is compatible with serializable transactions. It won't mess them up. But if everybody runs at these lower levels, they will go faster. All right, so that's read uncommitted. No read locks. You can read dirty data. Read committed says, well, I don't want to read dirty data. I just don't want transactions. So, look, I'm going to read committed items, but the minute I read them, I'm going to let go of my read lock. Right? And so I won't necessarily read items that come from a snapshot in sort of serializable history, but every item that I do read, whenever it got written, it was from a transaction that had committed. Maybe that's good. It's a little hard to think about when that might be bad, but, I read a transaction with 3 objects in it, And each one of those objects was written kind of by a different transactional time in history. And I have to decide if that makes sense. And maybe I don't care about how these three objects relate to each other, so it's fine. Right? Each one of them was a real transactional output just from a different point in time. Maybe that's okay. So that's read committed. The next one after that is called cursor stability, and so that ensures that reads are consistent while the application is thinking. So imagine you're an application, you say get next, okay? And while you're thinking, before you say get next again, you hold a lock on the last thing you said get next on. And then when you say get next, the second time, that first thing, the previous thing you're looking at is unlocked. All right, so while you're thinking, before you say get next from your cursor one more time, you hold the lock on the thing you just most recently read. So no one can mess with the stuff you're currently thinking about, is a way to think about it. That's cursor stability. Again, a little hard to know, like, is your application going to be correct in cursor stability mode? I don't know what your application is. Maybe your application like makes sure that people in a social network, if they have a friend relation this way, they also have a friend relation that way. Will it work in cursor stability mode? I don't know. Go figure it out. Okay. You have to figure it out every time for every application, whether this stuff makes sense. Repeatable read. All right. This one is commonly used. If you read an item twice in a transaction, you should see the same committed version of that item. But across multiple different items, you might see versions from different transactional rates. Okay? And the implementation here is you hold read locks until the end of transaction. So each object that you read lock might be written by a different point in time, essentially, in serial history. But that read lock, you do hold it to end of transaction. No one can mess with that object till you commit. All right? So that's sort of nice, because if you go back to read that thing again, you get it. Repeatable read, though, doesn't include phantom protection. So it is long read locks, long write locks. It's two-phase read and write locks. So you think it might be transactions, but it's not, because there's no phantom protection in repeatable read. Long reads, long read locks, long write locks, but no phantom protection. And then serializability is the whole enchilada. This is up, turn the DOM to 10. You have long read locks, long write locks, and phantom protection. Okay? So that's kind of the menu of modes you can get from traditional databases. And I can tell you what it means if you're serializable. You can pretend that the database is all yours and write programs like a normal person. And with every other lock mode, what I tell you is you have to think about all of the stuff it says on there and how it affects the semantics of your application. And it's not very easy to think about that. Right? And most people actually don't have a good sense that they have correctness when they write on top of this stuff. It's like very case by case and very hard to reason about. So those are the standard ANSI SQL isolation levels. Any questions on those? All right, they're based on how long you hold your read and write locks. It's that simple. So number one is no read locks, read uncommitted. Read committed is short read locks, just long enough to read the object. Cursor stability is somewhat longer read locks, as long as you haven't read something else. Repeatable read is long read locks and long write locks. Serializability, long read locks, long write locks, and phantom protection. Very mechanistic definition of what this stuff is. There's one more loose isolation model, though, that was invented at Oracle that's very popular, and that it attractively seems right, except that it's not. But it usually is. So it's a fun one to talk about, and it's widely used. It's called snapshot isolation. And the basic idea is that all the reads made in a transaction are from the same point in transactional time. So in essence, when you start the transaction, pretend you took a snapshot of the database transactionally. So you got read locks on everything you were ever going to read. It's all consistent from a single transactional point. And everything you do after that's based on that snapshot of the reads. All right? And if any of the writes that your transaction wants to do conflict with any writes that happen after that snapshot, you have to abort yourself. So you can't write stuff that conflicts with other transactions because your snapshot was old. So that sounds pretty good. And in fact, the way this is implemented by Oracle is with a multi-version system. So the snapshot you get has to do with multiple versions of objects, and they give you sort of consistent versions. So they give you a snapshot that are all from the same point in time that are conveniently located, essentially. So they have multiple versions of tuples on each page. And so they'll try to get you a snapshot where you don't pay extra IOs to go get the consistent versions. They'll try to get you a version where all the IOs you did for the pages give you consistent versions for some snapshot in time. Maybe not the latest, but some snapshot in time that's recent. Okay. So it's actually very cool. So first fact, surprisingly, this is not equivalent to serializability because those reads you do are from the past. They're from the snapshot. Right? They're not necessarily up to date, so to speak. Interesting fact number 2 is Oracle calls this serializable mode, which it's not serializable. Okay, so when Oracle says serializable, they mean something else, which is actually pretty aggravating. All right, so be it. So when Oracle says serializable, they don't mean what everybody else teaches and implements. All right, they mean snapshot isolation. Here's the problem with snapshot isolation. It's a subtlety. It's called rate skew. And the classic example is you have two accounts, checking and savings, and you have a constraint that spans those two objects. Constraint says that the checking account plus the savings account must be greater than 0. Okay? So here's a scenario where snapshot isolation is going to give us strangeness. So we begin with both of them having $100. T1 comes in to withdraw $200 from checking. T2 comes in to withdraw $200 from savings. All right, this should be a problem because we only have $200. We can't satisfy both of these guys, right? In any serial schedule, one of these guys will abort. Agreed? Okay, here's what happens. T1 before T2, T2 will fail because there's no money left in the bank, right? T2 before T1, T1 will fail because there's no money left in the bank. Snapshot isolation, they both get a snapshot of the database, 100 in checking, 100 in savings. The first guy says, hey, if I withdraw $200 from checking, the total aggregate sum of the two accounts is 0. Negative 100 in checking and 100 in savings, it's all good. T2 does the same thing except from the other account. Say, I'll take from that other account and then everything will work out. And the end result is that you had 200 taken out of checking and 200 taken out of savings. No write conflict, right? But because the snapshots were both at the same time and didn't reflect each other's rights, you get a schedule that's equal to neither serial schedule and violates the integrity constraint. Okay? Everybody good? So it's not serializability. But how often does this happen? You have to have constraints across multiple objects, la, la, la. It doesn't happen maybe that often. So snapshot isolation is kind of attractive. Postgres implements it as well, actually. PostgreSQL implements it as well. Okay, so here's some bad news. The lock-based implementations that I described don't actually exactly match the SQL standards. What am I trying to say? Right. The lock-based implementations achieve the ANSI standards. All right, so if you want the ANSI standards, those long locks, short locks, that thing will get you them. But the way they're described actually is more general. And so the official SQL definitions actually, in principle, could be implemented by, say, multi-version or optimistic concurrency control, but it's very unclear how to do that. And it's not even really clear what those standards really mean in a semantic sense. It's very confusing. So it's really hard even to understand the definitions of these weak isolation models declaratively, and even harder to understand how they relate to your application. And so the poor app developer really working with these kind of models is really at sea. They're given no tools to debug whether their application makes sense with these weak isolation models. So that's kind of bad news, right? We wanted to be able to turn the dial a little bit down without losing our application developer ease of use, and we didn't really get that. We really had a binary, it makes sense, or kind of it doesn't make sense in different ways. So you have to reason very carefully case by case to do this stuff. Here's worse news. This is from a recent paper by my student, Peter Bayless. He went and just surveyed the different database systems to see what their default isolation mode is and what their best isolation mode is. If you look in the default column, S is serializable. 1, 2, 3 out of those systems ships with serializability turned on. All right, VoltDB, which is one of Mike Stonebraker's startup companies. BerkeleyDB, which is not Oracle. It's Oracle's embedded database, all right, which used to be an open source project at Berkeley. And Ingress. Those are all shipping with serializability turned on. Everybody else is shipping with something less. Okay, fine. So out of the box, if you turn on a database system, it's probably not giving you ACID transactions. Beware. Okay, everything I taught you is not the default in most of these systems, which seems crazy, right? Worse, there's a bunch of these systems where you can't have S. They don't implement it. Right? And these are ACID transactional databases. They're not NoSQL, mind you. These are supposedly relational ACID databases. Oracle 11g. Nope. Can't implement serializability in Oracle. Sorry, snapshot isolation for you. Amazing, right? So some of these systems you can turn on serializability, but a bunch of them you can't. It just seems crazy. Like we sit here, we teach you about transactions. In the real world, they're not even turned on a lot of the time. And what do people get? I don't know. The answer is I really don't know. I don't understand how applications work without serializability. The answer is, and Peter Bayless did some work on this as well, if you go and you run a bunch of applications, or you try to model what interleavings are likely to happen probabilistically between different transactions, you can find out, under certain assumptions, what percentage of time bad things will happen, and the percentage is kind of small. So like 99.5% of the time, things will work out serializably anyway. And the other 0.5%, I don't know. Your database is corrupt, but you figure it out someday. I guess that's okay. Although people tend to use transactional databases for the stuff they actually want to be right, so it's kind of nuts. But that's the state of the world. All right. Be sure if you think you're getting serializability that you turn it on. Okay. Also be sure if somebody promises you that their database is lightning fast, that they're measuring it in a mode that you understand, right? Because you can cheat and not set locks and let things go concurrently and make things go faster. Make sure that the serializability setting is the one you want when you're benchmarking. Okay? So that's all I'm going to say about advanced concurrency control, although that filled most of the lecture. There are lots of other subtopics in concurrency control. So I could tell you about more isolation modes and semantics, which I won't. I could tell you about more ways to implement the ones you do know, like I could teach you optimistic concurrency control, different flavors of timestamp concurrency control. I won't. So those are sort of protocols. There's also implementations, like how should we really implement these things? Where do the disk writes go in multi-version? And how do we organize the versions on disk? Won't talk about that. And then different problem settings, so distributed transactions or transactions where the application actually gets to tell the database more than just read, write, and integrity constraints. They can tell the database data type sorts of things. Like this data type is a counter, and it only goes up. So I promise you that this thing will never go down. Right? There's all sorts of ways that you can change the transactions problem that people have explored. It's still an active area of research. So my student Peter Bayless is on the job market this year. He's like the hot thing. He's going to interview at all the best schools, and his thesis is absolutely it's about transactions. He invented a new isolation model and talked about distributed transactions. It's very relevant to all the new SQL systems. It's a very hot topic. So lots of renewed innovation, partly due to NoSQL and massively distributed databases, which we'll talk about, hopefully, time permits, next Thursday. Okay? So that's why I added this as the advanced topics lecture this year. Transactions are absolutely being revisited, and they're back. Okay. We have about 10 minutes to get an intro to the other piece of ACID, which we haven't done, which is logging and recovery. So we'll get an intro today, and next time we'll go into detail. No, that's not it. That is it. Oh, haha. Sorry. We're going to have to take it off the internet because I overwrote the lecture with that news flash. I forgot to re-download it. There we go. Okay, let's go back to the beginning, ACID. Remember, just a mnemonic, not like some sort of axiom system, just a mnemonic, but a useful one. So atomicity, consistency, isolation, and durability. We said that consistency is integrity constraints, so just ignore the C. The C was there just to make for a nice acronym anyway. I, the isolation part, is what's guaranteed by concurrency control to a large degree, which leaves us with A and D, atomicity and durability, all or nothing. Right? Atomicity says all or nothing. Durability says if it's all, it's really all. It's durable. Okay? And so recovery manager and the log manager are going to be dealing with atomicity and durability. And also, they're going to allow us to do aborts for consistency-related reasons. Okay? So here's the motivation. Transactions may abort. All right? We have to be able to support that. So for atomicity, making sure it's all or nothing, we have to be able to support abort, which is nothing. And then for durability, We have to make sure that the system remembers things even if it crashes. So let's just go through a scenario for a minute. Time goes from left to right. Crash happens at that point in time. T1 should be durable, yes? Agreed? T2 should be like it never existed, even though that abort happened before the crash, right? T3 should be durable for all time. T4, if the system crashes, we have to roll back T4, okay? We're not going to try to pick up T4 where we left off. We're going to just abort it. T5, similarly, all right? And notice the start time has nothing to do with anything. It's all about the end time. All right. Why does the database stop running? Give me an example of why a database would stop running or crash. Any old example will do. Yes, in the back. Power goes out, right. Yep, that happens. Happens at my house. Okay. What else? Yes. Hardware corruption. Disk could be even a CPU could blow, memory chip could fail, hardware fails. Disks fail more than most things because they're mechanical. Yep. Uh-huh. Say that again? It got spammed or DDoSed or something, and it's not available. Maybe it's running, but it's not responding anymore, right? So that's possible. Yep. It's not doing any useful work. What else could happen to a database that could cause it to fail? Operator error. Actually, one of the most frequent causes of failure in traditional environments. Oops, I said RM, tilde Joe H / space star, right? I deleted all your files in addition to my files, right? So other forms of operator error relate to the things we heard about. Operators routinely trip over power cables. Operators routinely break hardware. They routinely shut down machines without shutting down the applications on them. Operator error in the 90s was by far the most common source of failure, way by far. But hardware does fail, but and software crashes. We left that out. The database system just could have a bug and it could crash, and the operating system could just have a bug and could crash. And these things happen with some frequency too. Okay, so the order of frequency traditionally was operator error, software failure, hardware failure. Okay. In the era of the internet, 2000 and onwards, and with hosted services, operator error has gone way, way, way down because you don't let, people who make $120,000 a year as a sysadmin into the machine room anymore. They don't go to the machine room, right? So they don't trip over the wires. Moreover, if you go into a modern data center, there are no wires. You can't see the wires. The wires are all kind of under the floor and carefully configured up to the racks. There's all sorts of careful air conditioning to keep the machines cooled properly. Disk drives are pulled out from the front. All the operations are the front. You never go to the back of the machine and kind of reach around and do this. So all the crazy stuff that system administrators used to do, they stopped doing when this stuff became sort of farmed, right? And so in major hosting service, there's many, many fewer operator errors. They're all software operator errors, right? You never actually touch the computers anymore. Right? And in fact, even the operators of the data center, if you go into a Google data center, they're configured. These machines are actually built so that physical maintenance is done in a pretty error-proof way. All right. I won't say a lot more, but it's absolutely a science. The design of data centers is a science, and many people view the design of an entire data center the way we used to view the design of enclosure for a computer. So a lot of people who used to be in manufacturing and would manufacture the HP PC went into manufacturing data centers. How do you cool them? How do you make sure that you can't break them, and so on. So much less operator error than there used to be. All right. So the desired state after the system restarts here, T1 and T3 should be durable. T2, 4, and 5 should be abort. Okay. Assumptions we're going to make throughout our discussion of logging and recovery is that concurrency control will be in effect, particularly strict two-phase locking. All right. Just assume strict two-phase locking for the rest of the semester, which is only 2 more lectures after today. All right? And that updates are happening in place, so it's not multi-version. Data's overwritten on or deleted from the actual primary copy of the data. There's none of this kind of I keep a copy off on the side to myself and make my updates. Updates are happening in the buffer pool on the image of the page, and they get flushed back to the page. Okay? So, can anyone think of a simple scheme, a really simple scheme, requiring no logging or anything fancy, to guarantee atomicity and durability? I'm open to suggestions. Really simple. Doesn't have to be awesome, just simple. Okay. Yes? Do everything serially. Okay. That's a great place to start. So let's not worry about interleaving schedules. One transaction at a time, please. And at the end of the transaction, it will either say abort or commit. Okay. What if it says abort? How should we make abort easy? There's only one transaction. How do we make aborting a transaction really easy? How do you abort your VI session? Or Vim, I guess I should say. Well, you can turn off the computer, right? That usually successfully aborts your Vim session. You could say Control-C or something like that. Probably Vim captures Control-C, but you kill the process, right? That usually aborts your Vim session. Do the effects of your Vim session show up if you unplug the computer or you kill the process? They don't, because Vim doesn't save anything until you say :W return, right? Yes? They do have a swap file, so they keep a log. So it's fair. But they don't corrupt the data, right? So one way to make this easy, you can make abort easy by not overwriting the data until somebody says commit, right? So we won't write the data back to the database until somebody says commit. That'll be pretty easy. Okay, how do we implement commit? What do we do when someone says commit? All our data's in memory. They say commit. What do we start doing? We start writing the data back to the database, and I pull out the plug. Now you got a half-committed transaction. So it's actually not that simple. You still have to deal with commit being atomic, right? Because if you started writing it and I pull out the plug and you have no log, when I plug it back in, you don't know what stuff is good stuff and what stuff is dirty stuff because you had no log, right? So actually, it's still kind of hard. But what we could do is we could say your transaction can only update a single page. And then maybe it wouldn't be so bad because page writes are atomic. So that's one simple scheme. One transaction at a time. Don't write anything back till commit, and your commit has to touch only a single page of the database. Otherwise, the system doesn't work. I have a simpler system than that, though. It's called MarkerDB, right? And you submit transactions to this thing, and it doesn't do a thing at all, right? And it never corrupts its database. MarkerDB never, ever causes failures. It's also completely unavailable, okay, for transactions. But that is a design point. You actually, it sounds crazy, but you can make up like really complicated protocols where the moral equivalent is unavailable except in rare cases, right? Okay, so that's not good, right? We want availability in addition to all this other stuff. Okay, so I'll just point that out. Last thing I'll say before we go next time, well, yeah, that's probably the last thing we'll say, is that the buffer manager plays an enormous role because in a database system, when stuff is in memory, when changes are in memory, they're in the buffer pool. That's where changes in memory happen. And things get back to the database by flushing pages from the buffer pool. Unlike a file system where you might write things to a different place in a swap file or whatever, what we said in a traditional database is that the buffer pool is images of pages, and when you evict things from the buffer pool, they go back to where they came from, and the page overwrite what was there. So the buffer pool is key. Okay? And so there's two policies that we might want to worry about in the database. There's the force policy, which is on commit, before we return from the user's commit call, we're going to make sure that every update is on the database disk. That would be a force policy. That means in order to officially get a commit, you have to force all the updates for that transaction to the database. All right? That provides durability without any redo logging because we never achieve commit until all the pages have been forced to the database. Okay, so there's no need for redo logging if you do a force policy. But it can cause poor performance. Why? I say commit, and then what happens? What slow things happen when I say commit? To force all these pages out of the buffer pool back to the disk now, right? And they may be scattered all over the place on the disk. So it's a bunch of random IOs if it's a magnetic disk. So force is expensive. I'm asking you to do a whole bunch of writes in all sorts of different places now, before you tell me commit. So force is expensive. The other issue is whether you have a no-steal policy. So do you allow buffer pool frames that are dirty, they have dirty data updates in them, do you allow them to overwrite committed data on the disk. Right? This is, if you don't allow dirty buffer pool frames to be written to disk, that's like saying no one can steal a frame from the buffer pool unless it's clean. Right? Dirty frames can't be stolen in the buffer pool by other transactions or by other reads. All right? So if you have a no-steal policy, dirty pages in the buffer pool must stay in the buffer pool, well, then that's nice, because then you don't have to do any undo logging, right? Because you never write any dirty data. You only write data from transactions you agreed to commit, all right? But that can cause poor performance. Why can it cause poor performance if we don't write buffer pool pages till later? Yes? What's bad about no-steal policy in the buffer pool from a performance perspective? Well, think about your replacement policy. What pages are you allowed to replace? They have to be unpinned, of course, and not dirty. So as transactions are going and making updates, they're using up pages in the buffer pool, and now I'm not allowed to replace them. I'm not allowed to steal them, right? So you can get to a point where all the buffer frames are being held by transactions that haven't committed yet, but they're dirty, and there's no buffer frames available for me. All I wanted to do is reads, maybe, but I can't bring my pages into the buffer pool because there's no frames that aren't dirty. So no steal can start to leak buffers. Buffers are sitting there in memory, and they're just waiting for someone to commit. So ideally, what we really want is a no-force steal policy, right? We want high performance. So we want, in the end, to get steal and no force. So we're going to not have to write, when you say commit, I'm not going to write anything to the database right now. I'll do it later. And I'll say, sure, you're committed. And when you say that you've updated a dirty page in the buffer pool, I might flush that to the database any old time. I'll let the buffer pool decide that. But the buffer pool is going to go ahead and write dirty stuff back to the disk. If we do both of these things, we have a lot of problems to deal with, but it'll go fast. And so this is going to be the challenge for next time. How do we allow for a no-force policy, which means commits don't appear to have done all the durability stuff, and a steal policy where the atomicity stuff seems to be broken. We're writing half transactions to the database. So it seems like we're violating durability and atomicity, but we still want to get the right answer. All right? And that's what we're going to try to achieve next time. So it's very ambitious. We want all the performance of a broken system, but we want it to be correct. Okay? And that's what we'll work on next time. All right, I'll see you in a week. Thursday is Data Science Day. Homework 5. One brief announcement. Homework 5, you may recall from the description, part of the grading is peer grading. So you guys will be grading anonymously each other's homeworks. And in order to make sure that we get all the grades done, part of your grade is determined by you doing this on time. Okay? So you will be contacted on Thursday with the homeworks that you have to grade. It won't take very long. But if you don't get it done by Sunday, you will lose points on your homework. Okay? And there will be Piazza posts with lots of details.